I hope you had a good weekend. Was there anything Halloween oriented here? Were there Halloween festivities or Halloween parties, or at UCSD we had a pumpkin drop for some reason that has been going on for 40 years. The physics department would then go and measure how far I guess it was on an exam or something. How far out does the pumpkin? Now that I'm thinking about that, I'm lying. It's a watermelon drop, and it wasn't in Halloween, but in any case. So we left off on Wednesday talking about RNNs, right? RNNs stand for recurrent neural net, right? Here, this is the hardest way one can have to read this. It's like a very high-scoring Scrabble input. Yeah. So recurrent neural nets. We talked about backpropagation through time, which is the fancy way of doing backpropagation because of the fact that we went forward, right, sort of through time, where time is really whatever our sequence of inputs are. And then when we do backpropagation, because of the fact we had this recurrence where h of t is calculated with respect to h of t minus 1, when we're computing our weight matrices, for example, for the HH matrix, we've used that same weight matrix multiple times, right? So we used it at time step 1, at time step 2, at time step 3, all the way to time step t minus 1. And when we do backpropagation from time step t, we've got to go all the way back, all right? But it's just backpropagation. The backpropagation through time, I want to mention something about that, and really, what I'm really going to say is, what we're talking about is truncated backpropagation through time. Because we've got a bit of a problem. If we want to do backpropagation, then we need to keep all of our activations, right, at each time step. Otherwise, we'd have to do a ton of recalculations. So we need to keep each of our activations at each time step. So we need and this is during the forward pass. In order to do the backpropagation effectively. The problem is, how much data is that? If we've got, let's say we look at ResNet 34, how much data needs to be saved in the forward pass in order to do a backward pass? It's a lot, but it's about 34 layers, right? Because it's a ResNet 34. And depending on how we're counting that layers, there's no more than that, right? So we're really counting the convolutional layers. So there are some others in there. But there are, let's say, 61 layers that we've got to keep. So that's 61 activations that we've got to keep. Straightforward, right? When we're on the GPU, we basically have that amount of memory, the number of activations, times what else impacts how much space we're using on the GPU? We're not doing time steps yet. I'm just back to a CNN, so regular old ResNet 34. So we've got the number of activations we've got, right? That data. And what else do we have that is affecting how much space is used on the GPU? So we're on the GPU. We've got some memory. And we've got, let's say, enough for 34 activations. And then I claim we've got some others here. And this is what? We got the weights and biases too, but the key thing to remember is we are trying to use up all of the GPU's memory. And so one image is not enough. What do? We have a batch of images, right? So we've got the batch size sort of by here. And this is the memory per batch. Batch size is fixed, right? We set that up ahead of time. We normally don't ever change it. The memory that we need per batch is also fixed. So the product is fixed. We look, we see what fits in memory. If it doesn't fit in memory, what do? Reduce the batch size because we don't have control. Unless we want to change it to a different architecture, we don't have control. It's because of this memory issue that you'll see that sometimes some of the newer GPUs have the option to do 16-bit arithmetic, 16-bit or even 8-bit arithmetic as well. And the reason for that is not speed. It's so that you can store less memory, which means your batch size can be bigger. Okay. There's some issues there just because it kind of quantizes your numbers there when you have fewer bits. All right, so when we are doing RNNs, we still have batch size. Okay? That is, we'll be looking at if we're translating English to French, we'll be translating different English to French sentences. Okay? But the problem is, or the question is, what about this here? What is that amount of memory that we need for a single sentence? How big is it? And what's it depend on? So how much memory do we need? Or really, how many activation layers? Or really, we want to say how many activation time steps do we need for some given x? You know, x sub 1, our first input. And what does it depend on? The number of words in the sentence. The number, basically, right? The size of x1, the number of words tells us how many time steps we're going to do. We saw for RNNs it can be one to many, many to many, you know, and so on. But in this case, let's just say it's many to same. Okay. So the back propagation through time, if we want to do 100% correct back propagation through time, we've got to go from the very last time step back to the very first time step. And that could be somewhat large if it's a sentence. What's the largest length an English sentence can be? So what's the largest integer we can have? And this is the game. Have you ever played this with like a 6-year-old or a 5-year-old? You say, well, tell me your biggest number. And then you give them a slightly bigger number, right? And whatever number they say, I know you guys can all come up with a larger number. Okay? The same thing is true for sentences. I claim whatever sentence you give me a sentence, I can always put in front of it, let's say, I thought. Okay? It might not be a completely sensical sentence, but it's certainly grammatical, right? I thought it was grammatical. I mean, I thought it was grammatical, and so on. Okay? So we have a problem because it has to be arbitrarily large. So the solution is truncated BPTT. So truncated BPTT says don't keep it all. Just keep the last K2 layers. Okay? So we have our very long sentence. he thought. Okay, and so we break it up into chunks. And let's say, I'm going to just make it 100. Okay, so I'm going to say I'm going to run this for 100 time steps. And we start out, we have our H1, we have our H2, we have all the way up to H100. And then we do backpropagation all the way back 100 time steps. So we know exactly how much data we need to save on our GPU. It's these 100 activation vectors, plus our weights and our biases and so on. But that's what we need to do our backpropagation. Once we finished our backpropagation, we're saying we're never going to go back to this. We're going to throw away our activations. And we're going to start with this bunch. Okay? There are several ways to implement this. Right? One way is you can kind of have sort of in your neural network, it knows where one starts and the other stops. Or a more straightforward way to do it would be to say, let's just look at this as a brand new batch. Do we want to have the state information from here? Would that be useful as we're working with these words? Yes. The entire state that we need from here is captured in H sub t, or H super t. So we just need to feed in H super t here. You know how we normally, when we start out, what do we do when we feed in? What's our H0 as we come in here? Yeah, we just know all zeros because we don't have anything better to do. Well, what we can say is let's go ahead and make this parameterized so that we can feed in whatever hidden state we want whenever we're starting our forward propagation. So here, what would we like to feed in at step 101? We'd like to feed in our hidden state from step 100, which we just did. We just did this batch. We save that information. We throw away all the others, and then we start fresh from here. Go, 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 go. Keep saving each of these activations till we get to the end. Backpropagate a fixed amount, of what we might call a truncated amount.
Is there a reason we don't like always store the last 100 at any point in time and then shift out old values?
We could shift out old values. I think it's
I ask only because I feel like with this model, if you say accidentally choose a truncation size that's like coincides with something in your data, then you would that could cause weirdness with backpropagation because you wouldn't be able to communicate like periods that aren't on those discrete time steps.
So that's an interesting point because we're not propagating, let's say, from here, backpropagating from here into our weights in here. And as you point out, if we did a trailing 100, then we could get information backpropagated from here into here. I have a solution for your problem, and I think it'd just be easier to code if we use this approach. So the solution to the problem is, so we're going to be training on these batches multiple times, right? And the solution is, as we train, we want to jitter the batches. So if we did 100, 100, 100, kind of our first batch, maybe what we want to do is 95, 95, 95. Or maybe some of the time, a small fraction of the time, 60, 60, 60. And so that we break up where these are happening. Does that make sense? Yeah.
Yeah, I guess kind of like related to that point, I'm just curious. So if we kind of do this, in certain chunks, how do we convey the information back to say the first few words in back propagation step, right? If
So
something of R depends on the context from earlier. If we do this truncated version of the back propagation, how are we conveying that information?
we're definitely losing information. So we are losing the ability to pass back information from, we had something here that affects our computation here, we can't get it past because we can't go more than 100 time steps. And there's no particular solution except to point out two things. One, we're going to see it's very hard to push information back a really far way. We're going to come up with some ways to do that. It's sort of a trade-off between how much training you can do. Right? If you want to make this larger, you cut your batch size, which means for a given amount of time, you have less data you can process. And clearly, for some of the stuff we're going to be working on, like if you looked at the collected works of Dickens, let's say, well, to create a language model, you really just look at that as one giant string. You clearly are not going to want to backpropagate through that. Jake.
You're saying like every Q1 steps through the forward propagation, and we do the backpropagation. When we were doing the backpropagation, we needed like the error of the loss function
Yes.
to get the very furthest in the future. So what do we do for that final layer when we've done K1 time steps, but we don't necessarily have our final output?
So, and in this example, K1 and K2 are both 100. We can look where they're not the same. So let me see if I understand your question. When we get to here, we need to do backpropagation. In order to do backpropagation, we need loss. We don't have a loss because the loss is across the entire sequence. We use the loss we've got so far. So we're going to have a loss so far. Okay. Other questions? And I guess, so we saw the case where you wanted to come up with a image and then was it an image? No, it was text, sentiment classification, right? So you had a bunch of text and then you just wanted to know, was it positive, was it negative? So let's think about that for a second. How would we do that? Because there, if you remember, right, we had x, 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 and then one final yt, which is either 0 or 1. So that's a good example. How are you gonna get this loss until you get this? And really what we'd have is we'd have a y out here with that same fully connected set of layers. Yeah. And so it's just so far from what you've seen. What do you think the sentiment is? And then, okay, now that we've seen 200, what do we think the sentiment is? Even though we're only going to backpropagate to here. Keeping in mind, when we look, well, let's say at the very end, at the sentiment, we do know, we have seen all the words, and all the words have affected the state we have right now, right? Because T1 affected T2, affected T100, and then we passed T100 back into T101. And came all the way. Oh, yeah.
You said that this is how we use K1 equals K2. Is the motivation for sometimes having K2 or possibly frequently having K2 be greater than K1 to sort of deal with the fact that after this connection that's where you're losing the most, so you have to pay through them? I guess I'm not questioning how K2 being greater than K1 analogizes well to how you discussed thinking that it has separate batches.
Well, yeah, so then it is less a separate batch. Then it's really less separate batches. But we don't have seams. Right? We don't have the big seams we'd have otherwise. So let's say we're doing a K2 of let's do a K2 of 150. I'll do that in green. So the first place we would do a backward propagation, right, would be here. We do a backprop at time step 100 because K1 is still 100, and we would look back 100 time steps. What's the next time we would do it? At 200. So we do a backprop here, and we go back how many time steps? 150. So we would go from here to here. So the nice part is we no longer have this seam here, right? We are taking into account stuff from the future into here. And then the next or last one we would do was at time step 300. Go back to here. In prac, I don't know. I would say the most common is K1 equals K2. Okay. So, other questions on this? All right, bidirectional RNNs. So we're going in this direction, right? H1, H2, H3, and we're taking into account X1, and we're spitting out. And the question is, well, sequences have not just one direction, they have two directions. So why don't we, as well as looking from left to right, look from right to left? When we talk about time steps, it sounds like you're going backwards in time, right? So we're talking about looking from time step 1 to 2 to 3 to 4 and so on, but also looking back from time step t to t minus 1 to t minus 2 to t minus 3 and so on. Why would we want to do this, and when could we or could we not do this?
Maybe if you were like building things to predict the words in the sentence, like if you have a blank somewhere in the middle of the passage, you can use later information to fill it in.
If you're filling in, and this is often something that is done, if you have a sentence with a blank in the middle and you want to know what should go in that blank, then it would be useful to have not just the words before it, but also the words after it. That's actually a common thing that is done with language modeling where you don't have labels. So instead we just say take some unlabeled sentences and just try and blank out a word in the middle and predict that, and and try that for all the words in the sentence. So.
You can also use it if you want to understand the context of a given word, and maybe later words influence the context of that word.
Sure. Context certainly include context. We don't define context of a word as the words before it, right? We define context as the words before and the words around it, right? So that is certainly a case. If we look at remember one of the problems we came up with the many to same was parts of speech. All right. So I thought John gave the orange. John is what type, part of speech? Noun, verb, article, right, and that's the key. This is either a noun or an adjective. And what do we really want to know? We really want to know what that word is, right? That would help us quite a bit in knowing what that is, right? So if it says tabby, then this would be an adjective. But if it says to, like to Sally, then that would be a noun. When can bidirectional RNNs just not work? Real time would be a good example, yes. If you're doing it in real time, you can't know what the future is yet. You have to wait for that. And if you've got to emit your y hat right now, you've got to emit your y hat now, and you can't wait for the future to happen. So that'd be a good example. So like speech recognition, maybe, right? Maybe or maybe not. It depends. We can get to that, yeah.
It doesn't seem like it would make sense for like any of the one. It's like, why would you have to go forward to back? How complicated it
Yes. In fact, as we look at our definition of bidirectional RNNs, all that the bidirectional really is going to affect is our output. So the only things we have are output and our hidden state. And our hidden state, well, we'll see an example in just a moment. So yeah, if you had mini to 1, you will have seen everything by the time you get to making your decision of what to output. If you're trying to do an Alexa, Alexa, what time is it? Would that be one where you could or could not use a bidirectional RNN?
I don't. Like, you can use a bidirectional if you don't want to output text up until the user stops speaking. So if the user stops speaking and then you want to output text, then you could use a bidirectional RNN because you don't have a real-time stream.
How do I know the user's speaking? I have a microphone. I'm just listening to shit, right? I know the user speaks because I have a neural network that tells me they're speaking. So,
how do you stop though? Yeah, maybe you can kind of understand when the user stops speaking, and then you can pass the
you could. Alternatively, what you could say is, what's the latency that a user is willing to accept as one or even can perceive, right? So if they can't perceive 100 milliseconds, then I could certainly take trailing 100 milliseconds and within that trailing 100 milliseconds use a bidirectional RNN, right? And then just keep moving that forward. So, but in general, yes, things where you have to decide stuff before the future happens is in real-time things is really where this doesn't work. And the other problem is memory in terms of how much is there in the future and how much are you going to take into account. So if we do, the works of Shakespeare and we're taking all of that as one big input, we have the same problem I described before of we don't have enough space to do that. So, all right, so here's here is our unidirectional RNN. Right, we've got x1 feeds into h1, x1 along with h0 feed in to compute h1, and that then outputs y1, and then we feed h1 into the computation of h2, feed that in the computation of h3, and then it doesn't go anywhere because we're done. So what we do for a bidirectional is we're going to say, let's have another state. So the backwards, right? So what I've done is I've used h, right arrow, to be our forward direction, and h, left arrow, to be our backward direction. So we'll call this 3 and 2 and 1. And what connections do we have? Well, which one's computed first? Commit. The lowest. No, because we're going backwards.
No, I meant the lowest from forward, but then
Oh.
the first.
Okay, yes. So here we know we compute first h1, h right arrow 1, h right arrow 2, h right arrow 3. For the ones I just wrote, which one gets done first? Yes, so this one gets done first. Calculate it first. And what information is needed to calculate h left arrow 3? x3, so we'll need that. What else do we need? We don't need y hat 3. And we need a 0 input, right? And then what are we going to be outputting? We're going to be outputting, we have to have some combination, basically, that happens here, where we combine the two hidden states, the forward hidden state and the backward hidden state, to compute our output. And then we do the same thing here and here that we're combining our outputs, and we need the inputs. And we're passing. So our forward activation goes from the top. Let's look at this. Our right arrow, so we have forward goes up, and our backward, BPTT, goes down. Agreed? Because our forward activation, our right arrows, our forward pass is computing this, then this, then this, so we're moving up. And when we do backward propagation, we go back the other way. And our reverse computation, our forward pass is going down, and then our backward pass, which is backward propagation still through time, just in the other direction of time, is forward in time. So actually, this isn't backward propagation through time, this is forward propagation through time. Does that make sense? Okay, yeah.
It seems like this would be particularly difficult to do our batching with, because like you would need to somehow have it. I guess we could just do multiple passes.
Yes. So yes, it gets to, it'll be complicated. Agreed. So our formulae really are our H sub t right arrows are just the same as they were before. We're just throwing right arrows on top of everything. And then we have a left arrow H sub t. And we're going to use the, I suppose we could have its own activation function. It's likely going to be the same. We have its own weight matrix, its own HH matrix, its own HX matrix, and its own bias vector. And the output now is going to be a combination of a activation function applied to a linear combination, right? A weight times our forward hidden state, and a different weight times our backward hidden state. Okay. Questions on that? And then we're just, for our recurrence relation, to initialize, right? Right going h sub 0, or upwards going h sub 0, starts at 0, and the downwards going h at t plus 1 is also 0. All right. Questions before we go on to gradients?
In practice, would you want to weight like the forward direction or the backward direction, or like?
I don't think there's any need to. Well, first off, in the weighting, the only weighting we have would really be the output, right? And if one of them matters more than another, that should be affected in these weight matrices that get learned. So we would imagine that that would take care of that. That make sense? Okay. All right, now we get to vanishing and exploding gradients. So vanishing and exploding gradients. If you remember from Wednesday, when we wanted to compute dl dx, sorry, not x, d h1, we had to compute dl dht times dht minus 1 times all the way to dh2 dh1. So we've got a bunch of multiplications, right? T such multiplications. And that can get exponentially smaller and exponentially large if those gradients are either small or large. Whereas small, I'm meaning between 0 and 1, let's say. And large if they're larger than 1. And of course, the size of t is going to depend on how much the exponent is. So that's our problem, right? And that's what we really talk about when we talk about the vanishing or exploding gradient. The gradient either gets driven to 0 or it gets driven to infinity. right? How does 0 show up numerically as we're doing our work in PyTorch? What number do we see? Our vanishingly small, exponentially small gradient is going to basically just show up as 0, right? We'll see it go to 0. What about an exponentially large gradient? What would that go to? We'll get what? Overflow error. And how does that show up in our IEEE floating point that everyone uses these days? Not a number, okay? So there are lots of different ways you can get not a number, but one of the ways is this. So if you start getting not a numbers, you've got an exploding gradient. If your thing's just not training, then that might be due to a vanishing gradient, right? Your weights are just not pushing back and it's not learning. One thing to point out, and we saw clearly as we were looking at computing our gradients, that there are different paths from the loss to particular areas of your network, right? So for instance, we have the loss composed of, let's say, y hat t minus 1, all the way to y hat, let's say 1. And if we've got some h of L here, how can the gradient flow to h of L? What's one way the gradient can flow to h of L, given, of course, that we have HL plus 1, etc. Or the reverse way to look at it is if we were to change h of L and bump it up by epsilon, what are the ways in which the loss would change? Give me one way, one path from HL to L. To where? Okay, so to y of L. So we would go over to y of L. Right, so here we're at y of L. L, I can see, was not a good choice to use for this since we're talking about L, our loss, but that's one way, right? So that is a forward path by which H super L can affect the loss. And therefore, we have a gradient coming back. What's another way? HL plus 1, and then y hat plus 1, and then up there. Or, I'll add another one, right, like that. Or, finally, up to HT and over and over. So we get a lot of paths, right, by which we can get here. And having these multiple paths, the way that vanishing and exploding gradients work is different between the two. So in order to have an exploding gradient, how many of these paths need an exploding gradient? Exactly one, right? So if one path causes an exploding gradient, then the entire gradient is exploded. Because it's just a sum of the gradients for all the paths, right? However, what about vanishing gradients? How many of these paths do we need to vanish in order for our final gradient to have vanished? All of them, right? As long as we're getting some path that's pushing that gradient, we're going to be able to update this. So DL, let's just say N for a neuron, vanishes if the gradient on all paths from L to N. Vanish. Okay? And that's going to be key for how we're going to try to address the vanishing gradient problem. Any questions on the problem? All right, so let's come up with one solution. This was an entire paper, relatively recent. I think it was, yes, 2015, by, I think these are doctoral students of Hinton, right, who's been around forever. And basically what they said is, you know, initializing the weight matrix, the HH weight matrix, to an identity matrix is a very good place to start. In fact, we don't need tan H, and we can talk just a little bit about why we have tan H, but we don't need tan H, just use a ReLU. Works pretty darn well. Why the identity matrix? Because what? Yeah, basically, I said if we're less than 1, we vanish, and if we're more than 1, we explode. And as learning happens, we may tend to get one or the other of those. But at least our default is we're going to be able to push the gradient all the way back. Does that make sense? Okay. Because when we're doing our backward propagation, remember, we have this multiplying by the transpose of the weight matrix. And so by multiplying by the identity matrix, as we're going backward, we're just keeping the same gradient going from one step to the previous step to the previous step to the previous step, assuming we don't have any other error coming in, like from the y hat at that time. Okay? So in general, you should do this. Just initialize the HH matrix to identity and initialize the bias to 0. Okay? And lots of packages out there just don't do stuff like this automatically.
So is this like a trade-off with our normalization techniques? Because like in normalization, don't we want to like kind of randomize the initial weights so that we don't train certain weights just in the second?
So I remember, and I'm just trying to decide how I'm reconciling that for a moment. I don't have a good answer for you right now, but I'll get back to that on Wednesday. All right, step 2, what we can do. We can do gradient clipping. So gradient clipping will not help us with the vanishing gradient, right? But it will help us with an exploding gradient. So the idea is, if the gradient's too big, just clip it to some value. So we calculate dl d theta, and we subtract the learning rate times that computed g from theta. Between here and here, we check and see how big it is. So there are a variety of different ways to do this. Reducing the magnitude of it by whatever way you do it works pretty well. So let's give one way to do it. We check and we see whether, right, the length of it basically is bigger than some constant v. And if it is, we go ahead and rescale it so that its length is g. So what does this do with the direction of the gradient? Does it change it? No. All it does is just change how far you're going in that direction. And so it says, instead of just going like hell in that direction, just go a little bit, right? It's like a governor on the throttle. Does that make sense? Yeah.
That equation reminds me of some kind of, like, is that just scaling it? Or is it some kind
So yeah, basically what we're doing is we're saying, let's say we've got 1, 3, 7 are our values in a vector, right? And we want to scale, so the size of this, let's make numbers that work really well. Let's do 4 and 3, okay, because I know those work well. So what's the length of this vector? 5, right? Because basically, Pythagorean theorem. So the length of this equals 5. And let's say we want to scale it so that it is no bigger than, what do we want to do, 3? So we want its length to be 3. So basically, we would multiply everything by 3/5, right? So we'd end up with 3/5 of 4 and 3/5 of 3. And then we have a total length of 3. Does that make sense? Okay. So this is one way to do it, and this seems like the right way to do it, right? We know we're still going in the right direction, where we want to go. Another thing we could do is we could say, well, let's just, instead of looking at the entire direction, scaling everything, let's just find those gradients that are too big, right, with respect to some particular parameter. So we looked at a bunch of parameters, and they're all 1s and 2s and 4s and 5s, and there's one that's 95. Okay? And we have decided 95 is too big, 20 is our maximum. So let's just take that one that's 95 and clip it down to 20. And we'll leave all the rest exactly alone. Are we going in the right direction? Are we going in exactly the same direction we were going before? No. Okay? I'm going to show you in a moment why that's probably okay. Let me give you another example. You find your gradient's too big, and here's what you do. You decide the maximum gradient I want is 20. I'm going to randomly go in a direction 20. Okay? And the theory is you're going to get away from wherever this high gradient is to someplace more sane. That last approach sounds silly. It's like, why would you ever do random? But let's say you go calculate, and you find that your gradient is not a number. Well, you know, or you have multiple things that are not a number. What are you going to do? So the idea is you just don't know. Pick something. Let me give you. So let me try and explain this. So this is from the deep learning book. I have referenced that in the syllabus and schedule, and it is a good book, and it's available online for free, although it's a little hard to search in the online version. So this is from that book. So here's the idea. We're down here, and we are moving dot to dot to dot to dot. Okay? And what we've got is kind of a cliff here, and then a little, what do you call that, a ravine, I guess? A ravine here. And we're trying to get to the bottom of the ravine. But what happens is, on this last step, we go a little too far in the ravine direction, and all of a sudden, we're on the cliff slope. Hold on just a second. I'm going to ignore that dot for just a moment, okay? So if we get past the ravine onto the slope, we'll clearly have a very high gradient, right? The slope is very high. So it's going to shoot us, if we're somewhere on here, is it going to shoot us to the left or the right? It'll shoot us to the right. But if the gradient is really high, it's going to shoot us way over here. And so we've lost, right, a lot of ground. And in fact, every time we come back in here, that might happen, right? Where we come, we go a little too far, and then we get shot back out. By using clipping, what can happen is when we get down into here and we get up on the ravine, we only go back a little amount. So we don't get shot way back over here. Okay. So gradient clipping is a very reasonable way to deal with exploding gradients. We've still got the vanishing clipping problem, vanishing gradient problem. Questions? So there are two clever approaches to dealing with vanishing gradients and RNNs. It is not unlike ResNet, right? Where in ResNet, we had these skip connections that allowed a way for the gradient to propagate back. And we're going to have the same idea. So the idea was first developed with this LSTM paper, I think it was back in, it was some time ago, like 20 years ago. And the GRU is more recent. So the LSTM stands for long short-term memory, which I think is a crazy name. I mean, I understand long short. Maybe long slash short would make more sense. So the idea is we're going to add some new state information. We already have our hidden state, right? We're going to also add a memory cell. And this memory cell we can maintain for long periods of time. It's not going, so the hidden state gets transformed each time, right? We go through a new computation of the hidden state based on the old hidden state and based on the new input, and we do a nonlinear activation, and then we go through do that again and again and again. It's kind of hard for a RNN to just, let's say, maintain in one of the neurons. I just want to maintain a 5, because 5 means we saw a masculine noun here. And much later on in your sentence, you might want to have a pronoun that refers to that thing, coming up with a particular example. So that's a little bit hard. A LSTM memory cell makes it easy. So we just have a memory cell and we say, at this time step when we see a masculine noun, kind of write into the memory cell. And then you can be reading that memory cell whenever you want. And you can take an explicit action then to change that memory cell. So it allows a way to, it's really one and the same thing. One, it allows me to pass information from a very much earlier time step to a later time step, similar to how in a ResNet we could pass information from early in the network to later in the network unchanged. And the flip side of that is gradients can easily propagate backward, which means we can learn it. So let's look through how this works. Does the idea make sense of having a memory cell in addition to our hidden state that we can read and write information to? And it's really every hidden state, we have a shadow memory cell. So whenever we're doing our computation within our neuron, we've got not only our hidden state, but we've got a memory cell. And so let's say we have our H at t, which contains some values, and we have our memory cell at t. When we go on to time t plus 1, we have lots of computation to compute h at t plus 1. But m at t, there is a path where it just directly can go across to m at t plus 1. And that's what memory is, right? Memory is this thing that maintains its state. The hidden state keeps getting updated all the time to reflect new information, new reality. The memory stays. So we've got our new state, our internal state, m at, let's say, t minus 1. We have our computed state, and then we're going to have 3 gates. So a gate, you know, if we think of it electrically, it's going to either allow something to pass or not to pass. These gates are probabilistic gates. So they allow a certain amount. They're not probabilistic, they're fractional. So they allow a certain amount to pass. So if our gate is set to 1, it allows everything to pass. If it's set to 0, nothing passes. And if it's set to 0.5, half of it goes. And this is good because that's differentiable, right? So we can do our backward propagation. So we're going to have 3 different gates, all of which probabilities. So the forget gate, 0 means forget everything that's in M. Okay? So basically reset M to 0. And 1 means just keep it all. And if we wanted a decaying memory, we could set the forget gate to some value between 0 and 1, right? It would be exponentially decaying with the rate depending on this value. The input gate says let's look at an example here. And I have a correction here, I apologize. How much of A, which is our computed state here, is fed into M. So the hidden state can go into the memory state and get combined with the memory state, or possibly replaced. So if we wanted to replace our current memory with our newly computed H, or our newly computed A, we would set the forget gate to 0, meaning forget everything that's there, and our input gate to 1, meaning the memory now will take on the value of A. And then finally, how much of M will the output depend on? So if we look at y hat, how much of M gets fed into y hat? We will look at the equations in just a moment. But we've got a memory. We can write into it. From what gate controls the writing? Yeah, that's the input gate. And we get some fraction of A, our activation. We can read from the gate. Read from the memory. What controls that? Our output gate, right. And we get some fraction of M. The original LSTM, this is all they had, an input and output. Okay? And then a paper later on showed, well, sometimes it'd be nice to just reset, to have a way to just reset. And so that's why they added the forget gate. So then there's some argument as to whether a forget gate is actually necessary or not. But the forget gate, think of it as clearing M. Okay. Questions so far? Laurel.
Your clearing is also some fraction.
Yeah. Yeah, some fraction. And as we talked about, some fraction can mean we are ending up having a exponentially decaying memory. Right. All right, so here is our diagram for this. We've got our forget gate here. All right, so this is F. And that's the gate. And this shows, you know, it can be open or closed. If it's open, how much of MT minus 1 gets into MT? None. And if it's completely closed, all of it. And unlike normal electric, if it's halfway, then half of it goes. Right? So it's really like a dial. So this path is the forget path. So does that part make sense? Just ignoring everything else, some fraction of MT minus 1 makes it into MT. All right. Then we have got our, and let's actually look at the forget gate for a moment. It's between 0 and 1, so we want to use what sort of a function? A sigmoid. And so we're going to take a sigmoid of, well, we're going to have a weight matrix for the forget gate that's going to take our hidden state, our previous hidden state. We're going to take our current input, and we're going to take a bias. Okay, so we get to know what the previous state was. We get to know what the current input is. And that can help us determine do we want to forget or not. I'll give an example where we might want to forget. Yeah, you got one? Okay, doing sentence analysis, let's say, where every sentence is independent of every other sentence, and we see a period. Gee, let's forget what we don't need that anymore. That's a perfect example of using the forget gate. All right, now let's look at the input gate. So this just represents, right, our calculating A. So our input gate says how much of A goes into M. And it's going to get added to whatever is there. So if I is 1, how much goes? Should be all of it. Let's just check. Yes, all of it. And if I is 0, none of it will go. And if it's half of it will go. So if you wanted half your old memory and half your newly computed value, you would set F and I to both be half. And of course, we're not setting anything to anything. The network is learning what good values of these weights are such that it comes up with good F's and I's.
Just to understand, there's no particular reason why I and F have to be scalars, right? Like they could also be vectors. Like maybe you want to remember or forget this chunk of memory under this circumstance or this other chunk under this other circumstance.
In one sense, they're already vectors, right? Because H is a vector of multiple neurons. So these are multiple neurons. And so we do already have parts of our memory, really. You could extend it to this idea of having more than one memory cell.
These weight matrices that we have for these cells, are these kind of separate for each of the cells in our model, or are they kind of shared?
Just like the way we deal with WHH. WFH, WIH, WOH are all shared among every time step. Good question. Others?
So, and the hidden state is the thing that's doing all the remembering and forgetting.
Yes, that's the thing that's doing all the remembering and forgetting. Exactly. So, and then finally, our output, we have our hidden state is some fraction of actually our memory. Okay, so we're gonna see in a moment when we talk about GRU a simpler gated unit, gated recurrent unit. So here we have this relationship between MT and HT, right? And so we could combine them into one. You have a question?
What you're describing is like a single bit of LSTM, and you can imagine having like the vector, and if those sort of running in parallel, the math values would be the same. But
Bit I have a problem with, just because it is actually a number.
sure.
So
Like
yeah,
cell.
a single cell. Yeah, and it's exactly right as we look at HT. Right, is actually a vector for each neuron. So we have ht sub 1, ht sub 2, all the way to ht sub k for whatever k we want there, right? Which is a constant that we decide of how many hidden state values do we want? What's the size of that vector? And it so happens the hidden state vector size is the same as the memory vector size. And so, okay. So these are all calculated all the same way. They just have their own matrices, but they're all working on the previous hidden state and the current input. A is no different from what we had before, right? We're just taking the old hidden state, multiplying it by our HH matrix, taking the current input, and then applying often a tanh. So the new M super T, is forget state, forget gate, dot producted with M at t minus 1. So that's just that gate across the top, plus I times A. And then H is just our output state times M. Okay, so that's how we compute this. How does this fix vanishing gradients? Okay, because our whole thought is we want to be able to pass back gradient information from a time step in the future to a time step in the past. Let me show you. So I'm going to go back up here and erase this. As we look at the gradient, the loss, to time step t, what is the gradient from mt to mt minus 1? So d mt dmt minus 1 equals what? Let's actually pull up the equations if we want and just see. So m is equal to f times m of t minus 1 plus I times a. So there is a path, right, where we're going to be going through a, but we don't care about that right now. From here to here, it's a straight shot, right? We can just directly go back and we just have a factor of how much? F. That's it. If f is 1, what happens to the gradient as we go from mt to mt minus 1? It's unchanged. And we can just keep it unchanged. So the neural network, as long as it is setting f to 1, it could pass back the gradient as many time steps as it wants. And as long as we have one path where we don't have vanishing gradient, we don't have vanishing gradient. That's why this works, yeah.
Is there also a path, is there also a path to m of t minus 1 through h of t minus 1, like from a for h of t minus 1?
So we're going to have a path, right? Let's look, let's say in green. We have a path from here to here, right?
Yeah,
And then in the previous time step, we can kind of come up and go through. So we can go up and over. So there are other paths. Yes, we definitely have paths that are going through H's. But the key is we have a path that doesn't, like the ResNet, where, yes, we had these other paths that are going through the residual networks, but we could just keep taking these skip connections and have a unchanged gradient. Same idea.
Is f a discrete 0 or 1?
F is a continuous between 0 and 1.
So
Yes.
will it not still kind of, so even if we push it back, won't that factor of f still affect the t-1 gradient somehow?
Yes, the gradient from here to here will be exactly f, right? Because we just have f times mt-1, so when we differentiate, we just get f. So we are providing the neural network an opportunity to be able to push gradients back. Let me even back up a second. Ideally, what would f be when we first started training? One. So we initialize it that way, right? Initialize things so that we're likely to get an f of 1. Okay? We could do it in a variety of ways. We could just make this a big bias here. So that by default, to begin with, the gradient keeps getting pushed back. And as the learning takes place, sometimes we might not want that gradient to go back, right? Sometimes we don't want it to cross the sentence boundary. Well, you know what? As long as f got set to 0 or small there, it's not going to cross. So it can vanish, but there's the opportunity for it not to vanish if it's maintaining that memory. All right. I'm going to introduce you to the GRUs. So in a GRU, said that's pretty complicated. And we've got a lot of matrices to keep track of, right? That's basically more parameters, which means the network has more expressive power, which means it's easier to overfit, right? Plus, there's less stuff we can fit on the GPU because we have these more matrices, so on. So a gated recurrent unit says, okay, let's just simplify this a little bit. We're going to say we don't have an extra memory state and a hidden state. We're just going to have a hidden state. But we're going to still provide a mechanism where we can pass back a gradient. So we only have 2 gates instead of 3. One to reset and one to update. And so we can see the diagram looks much simpler. So when we compute A, and the way we calculate our gates is the same way. Okay, same idea. When we're computing A, our activation, we get a control over how much of the previous H to read or not. So, like if we were at the beginning of a new sentence, we might want R to be 0, because we don't want any of that old state, right? The old stale state. We want new state. And so we would just be depending on the incoming X, which would make sense again in this case where we have these independent sentences, and when we start a sentence, we don't care about anything else. And then we have a Z state that tells us the proportion of A or old hidden state to use to pass on to the next hidden state. So the R gate allows us to say how much of the hidden state are we using to compute the activation, independent of how much is that old state going to maintain to the next time step. Let's look at the equations a moment. So A gets modified, right? Now we're going to take the old state and we're going to Hadamard product it with our read gate. So we're going to take some fraction of our old hidden state to compute our new activation. And then we're going to take this linear combination of A and H to the t-1, right? Whenever we have the 1 minus Z times something plus Z times something, we're saying take 60% of this and 40% of this, or 90% of this and 10% of this, and so on. So we're going to take some percentage of A and some percentage of the old state. So here's my question before you leave. What is the dht minus 1 with respect to this path, right? It's actually the sum of all the paths, but with respect to that green path, what's the derivative? It's z. Z can be 1, which means there is a mechanism now for pushing back the gradient. The rest of the machinery is simpler. We can have a larger batch size. I know we're over. Just one last thing, project. So today I want to know about your project. And I've created a project Google Doc that I shared with you. And I'll go ahead and put it on Piazza. So I guess you have an optional team name. Is that what this means? Or you guys are the empty string? Yeah, no, they're the empty string, so this is the no characters team name. They do that so they sort first in the white pages. Okay, so fill this out, and then I would like to talk to you about, either in person or over email, about what project you're choosing. Okay, and you guys need a topic. You're going to combine. Okay, very good. See you guys on Wednesday.